Hello everyone! Welcome back to this series exploring the Calkin-Wilf tree. Today, we'll discuss the missing details from the first video, along with some new applications. Let's get started. Previously, we used two important features of the Calkin-Wilf tree, that every fraction is reduced, and every possible reduced fraction will appear exactly once in the tree. These properties were essential to our results, so we should prove them. First, we will show that every fraction is reduced. At the top of the tree, 1/1 is reduced. But what about its children? In general, we'd like to show that if a fraction is reduced, then so are its children, because this result will propagate down the tree. Formally, we will prove that if p and q are relatively prime, then p is relatively prime to p plus q. Equivalently, if p and p plus q have a common factor, then so do p and q. This version of the statement is easy to prove. If n is a common factor of p and p plus q, then it divides their difference, which is q. Swapping p's and q's, we have a proof for right children. And that's it. Now we know that since 1/1 is reduced, so are its children, and since they are reduced, so are their children, and so on. Next, we will show that every reduced fraction appears exactly once in the tree. Consider as an example the fraction 9/7. If 9/7 appears in the tree, then it may be a left child or a right child. But since 9 is greater than 7, there is no choice. This fraction must be a right child. And we can solve for p and q to find its ancestor. We'll repeat this process on 2/7. Since the denominator is larger, this must be a left child, and we can solve for its ancestor. Notice that with each iteration, the sum of the numerator and denominator decreases. So eventually, this process must lead back to an ancestor 1/1. So 9/7 is in the Calkin-Wilf tree, and since we constructed the unique path to 9/7, it must appear exactly once. Of course, there's nothing special about 9/7. The argument applies to all reduced fractions. This completes the two proofs. Now let's return to the golden ratio. We can use what we just proved about the tree to learn more about this number. In the first video, we considered a path in the Calkin-Wilf tree consisting of alternating left and right movements which, in some infinite sense, leads to the golden ratio. But this was only suggestive, as we have not yet defined what it would mean for a number to appear at the end of an infinitely long path. We can be more precise and examine the path analytically by studying its convergence. If we truncate the continued fraction to only include the first coefficient, then the corresponding path in the tree is finite and approximates the golden ratio. With 3 coefficients, we get a better approximation, and an even better one with 5. This sequence continues, and the values converge to the golden ratio. Additionally, if we emphasize the convergence along the path, we see that the movements from one to the next are the same. Each iteration of a left and right movement produces a better approximation of the golden ratio. What would happen if we performed these movements from the golden ratio itself? After all, there's no better approximation. Let's try it. We'll write phi/1 so that it is clear how to perform the left and right rules. First, a left movement makes phi/1 plus phi, and 1 plus phi is phi squared, so we can cancel a phi to simplify. Symmetrically, the right rule produces a similar looking fraction, which simplifies in the same way. As we may have predicted, this sequence of movements leads to the golden ratio again. Now we can make claims about this number. If it is rational, then we showed earlier that it must appear in the Calkin-Wilf tree. But from our path above, we know that phi would appear more than once. This contradicts that every rational number appears exactly once in the tree. Thus, we conclude that the golden ratio is an irrational number. This argument is slick, And notice that we did not need anything infinite. The proof only uses the properties of the Calkin-Wilf tree in finitely many rows. Let's illustrate another example, the square root of 2, whose continued fraction looks like this. The continued fraction corresponds with this path in the tree, with one final right movement and alternating movements in 2s. The first few convergents are 1 over 1, then 7 over 5, and the next is 41 over 29, which is already close to 1.414. Emphasizing the convergence, we see that the path between them is a right movement, then 2 left, and 1 right. Let's try the sequence of movements from the square root of 2. Here's right, left, left, and right. It looks like we've reached something entirely different, but we can multiply to clear the denominator, and indeed, this is the square root of 2 again. By the same argument, we conclude that the square root of 2 is irrational. There's only one caveat to this proof. When we assume that the square root of 2 is rational, shouldn't we write it as p over q, where p and q are positive integers? Why are we allowed to perform the left and right rules on root 2 over 1? To answer this, we should demonstrate an important property of the left and right rules. For a rational number p over q, consider scaling the numerator and the denominator by some non-zero number m. Then the left and right rules produce these fractions, which can both be factored, and the m's cancel. So the results are the same as if we didn't multiply by m's in the first place. This seems apparent, but it wouldn't be true if the left and right rules weren't linear in the numerator and denominator. For example, if the left rule was to square the numerator, this property would not hold. Since our left and right rules do have this property, we can use any non-zero m without affecting the results in the Calkin-Wilf tree. Choosing m to be 1 over q, we see that the form we used in our proofs was legitimate. Next, we return to the central slide of the last video, where we discovered that a path to p over q corresponds with a continued fraction for p over q, whose coefficients are the numbers of left and right movements along the path. This diagram only hints at the pattern, so let's complete the picture. The path traces back to an ancestor which is mk right movements away from 0 over 1. So the continued fraction ends with this coefficient. And since 0 over 1 is 0, this simplifies to fit the suggested pattern of coefficients. And remember, the coefficients also count the numbers of consecutive 1s and 0s in the binary representation of n, which is the term number of p over q in the Calkin-Wilf sequence. So far, we've only seen paths in the tree which end with right movement. If instead a path ends with left movement, our convention is that the coefficient m representing final right movements is 0. In the continued fraction, this makes the integer part 0, which is expected since the left rule creates proper fractions. We've seen before how the Euclidean algorithm produces the coefficients of these continued fractions. Can the algorithm produce a 0? Let's return to the example where we ran the algorithm on 9 and 7. What if instead we run the algorithm on 2/7, which is a left child? With a and b as 2 and 7, we write 2 as 0 multiples of 7 with remainder 2. Then the algorithm continues on 7 and 2. The values of q are the coefficients of the continued fraction for 2/7, and there we see the 0 produced naturally by the algorithm. So that's all I have for you today. I hope you enjoyed, and I'll see you in the next video.